This is Lab 5, Physics 2211, Lab 5. It's about the Slinkies. So, introduction. For this lab, we got to choose our own adventure. And for this, I chose the falling Slinky because it was provided inside of our Canvas assignment. So, for this experiment, we were provided a video of a Slinky falling, and we tracked the bottom of the Slinky to determine the motion of the Slinky. And the cool thing about the Slinky was that while it was falling, the bottom of it stayed put while the top falls. So we wanted to figure out why this happens. So we tracked the video to get the Y data of the bottom of the Slinky and created a model in Python to model the Slinky. So concepts used, we have Newton's second law, we have position update and velocity update, and we also have force of drag. So tracker. So this is the video, and this is what we had. This was the video in tracker. So you can see the bottom stays put, and the top falls down. And once the Slinky reaches its relaxed position, it starts falling downwards. So you see it falls down, 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 and hits the ground. All right. So you can see here I calibrated the calibration to Veritasium's height, which is 175 centimeters. Mass of the Slinky is 0.204 kg, which I found online. And the origin we set is just the bottom of the Slinky. Okay, for the coding. So we have our initial conditions. This initial condition we got off tracker. Our system mass. I think I put it different in the code, but anyways. We have g equals 9.8 like normal, and then we have a force of gravity, and we also have a drag coefficient, which is the trial and error, but I landed on 40. So coding, we split this experiment, the tracker, into two main parts. One, because before 6.66 seconds you have two forces acting on the spring. So like in the video, you have a force of gravity as it pulls down the top of the spring, but you also have a force of tension, which is what keeps the bottom of the spring set. So this is what we're modeling here on the coding. So you have your force of gravity and your force of tension, which is the opposite of gravity, and your F net should be 0. This is why the bottom stays put. And as you can see, if you plug all this in, your velocity doesn't change. We start at 0 velocity, and our position is going to be the exact same. So coding, this is the second while loop. So from 6.67 seconds to 9.533 seconds, instead of having a tension force, because now the Slinky force, which is the tension force, there's not going to be anymore because it's in a relaxed position. So we're going to have a force of gravity and a force of drag. So force of gravity going down, force of drag is going up, and basically, this is how we're gonna get model the Y position. So if we get F net, force of gravity, force of drag. Here's our force of drag formula, and then we plug it into the velocity, and then we plug it into the position update formula. So this code basically though was kind of ripped off from lab 2, I think, where we did force drag and we did projectile motion, but a lot of this was taken from that. So results comparison. So both models follow the same model, which is we see that both from 0 to 6.67 seconds, we're chilling, we're at the same Y distance, but after that we fall down. So the computational model shows a straight line, but tracker's more squiggly, and my computational model falls faster, but that's probably just an error in the drag coefficients. It's very hard to line it up. Sources of error, tracking is hard. The video was really hard because it was low quality, and there was 6,000 frames, so I had to click a bajillion times. Other factors that may influence the video, there's other surroundings. Maybe he pushed on the Slinky a little bit, maybe there's a little bit of wind, stuff like that. Discussion, does the bottom of the Slinky stay stationary? Yeah, it does. As you can see in the computational simulation, we modeled the bottom of the Slinky. and it started moving after 6.67 seconds. In the start, there are two main factors acting on the spot on the spring. There's force of gravity and the force from the spring acting as tension, which is against the gravity. So that's why it stays put, and yeah, that's why it falls after 6.67 seconds when there's no more tension.